I'm going to start by talking about that particular solution part, because I kind of told you there's more to it than what we talked about. So let's go back. I think I'm going to go back right to here. So this is analytical slide 3. So just as a recap, when we're talking about this, particular solution, what we're trying to do is find an equation that satisfies a differential equation. Right? We're trying to find a solution that satisfies a differential equation. If you look at this, as we did, we made the guess that our particular solution is some constant, which is kind of funny that it would solve this, but it does, right? If you apply the second derivative to a constant, that goes to 0. If you then are left with C3 subbing in for our TP, then it just says C3 is equal to T infinity. So that's our particular solution. That equation satisfies the differential, the ODE. So that was a really simple example where like the stuff on the right-hand side is all constant. And so it's not like especially interesting. So I want to give you some other examples, and these are like unrelated to the current example we're going through, but it's just like other versions of this that you can see, and so that you know how to approach this in a more like robust way. So let's imagine that we have these ODEs. I've put them down just as examples. These are differential equations that you might get by deriving something, like maybe you have a boundary condition where there's some heat flux, and it's a function of the sine or cosine or something like that. Or there's some other internal energy generation, and it's occurring exponential to the alpha x, right? There's these situations where you can end up with stuff on the right-hand side in standard form that's not just a bunch of constants. So then what do? So if you remember the rules I scratched out here, it was write the ODE in standard form, and then 2, guess a form of TP to be some form that's based on the right-hand side. So what do I mean by that? Let's look at the first example. So in the first example, this one here, we have second derivative of t minus beta t. So here, let's just say that beta is some constant. I don't really care what it is. I just wanted to note that there's a constant there. So you have beta times t and then equal to the right-hand side. Now the right-hand side has both a constant and some function of the independent variable x. So this changes our guess, right? We have to guess a little bit differently now. And what we're trying to do is guess an equation that when you take the second derivative of it and you subtract beta times that function. Okay, so what would that be? Well, we can guess on the right-hand side for this, let's guess that p of x is equal to, well, we see a constant on the right-hand side. So let's guess that there's some constant involved, C3. We see an x squared term on the right-hand side. So let's guess that there's C4 x squared. Now this is not quite sufficient because if we're taking derivatives and we just guess like the thing that we see, we might miss one of the derivatives. Right? There might be a term involving x or something that we miss. So you have to take the derivative of these terms and add it as well. So the derivative of a constant is 0. We don't have to add that. The derivative of x squared is going to be c5x, right? And then the derivative of that is just another constant, but we're already accounting for that with c3. Right? So we've guessed a form that is basically the right-hand side in all its derivatives. Okay? So that's what that would look like. Let's take, I'll show you how it works out later, but let's look at the other examples here. So on this one, TP, let's guess the second one. Right, on the right-hand side, we have sine of something, omega is a constant as well, beta is a constant. So we have a sine function. So what's our guess going to look like here? Well, we would want to guess, C3 sine of, let's see, what did I do? So sine of omega x, right? Because you know that a second derivative is going to have to involve sine of omega x in some way. And then let's look at the derivatives of this. So that'd be derivative of sine is cosine. So C4 cosine omega x. And why didn't I write like omega C4 cosine omega x? Because that's actually the derivative. Well, we don't really care what the constants are right now. We'll figure it out later, right? So we don't need to, at this point, anticipate what all the derivative constants are going to be. We just have to have a constant that identifies this group that we'll find later. Which is also why if, let's say we had cosine there, I wouldn't make it minus C4. It's just always assume it's positive. We'll figure out the sign. We'll figure out the constants later. All right, so that's the guess for that. So we're covering the derivative sort of indefinitely for that, sine or cosine. The last one, let's see, this one, Tp of x. Here we would guess, well, there's an exponential term. So we want to guess, I think, that form again. So that would be C3 exponential of alpha x. And then what's the derivative of that? Again, exponential. So we've covered it, right? We don't need to guess anything more. We've covered all the possible derivatives here. Any questions on this? It's a little bit tricky. Okay, so how do you actually do this? Now we have all these extra constants. This is a problem. We can only accept 2 unknown constants because we have 2 boundary conditions we can apply. We don't have 5 constants. So let's look at this, again, this example up here, and actually take it all the way through. So we've guessed this form. Let's actually plug the form that we guessed, this thing over here. Let's plug that into our differential equation. So we have d squared dx squared. Plug this whole thing in. So it's c3 plus c4 x squared plus c5x. Okay, that's the second derivative minus beta, again, c3 plus c4 x squared plus c5x. It's equal to minus beta t infinity minus x squared over beta. That's just the example we were taking. So the thing that you have to recognize here is that the different terms multiplying the x squared constant, those are what we call linearly independent, right? Meaning, if you think about this solution, anything involving x squared has to kind of be satisfied by anything else involving x squared. Like, if I have to be able to pick a value of x, and this equation has to be true regardless of the value I pick. So what that really means is that anything involving x squared can kind of be isolated as its own equation, right? That has to internally be consistent. Anything involving x has to be internally consistent. And so you can separate out these different equations based on the order of the term that's involved. All right, so let's write this one more step, kind of take this derivative. We end up with 2 times c4 minus beta c3 plus beta c4 times x squared plus beta c5 times x is equal to over beta. Sorry, my mic keeps cutting out. So what I mean here is now let's look at this equation. So we have like 2c4, beta c3 on the left-hand side. That's stuff that's constant, right? There's no x involved in that. So this stuff here, let me get a color. So red, this stuff here has to be equal to anything on the right-hand side that's a constant. Right? This is, again, a tricky concept. It's confusing, right? But if you think about it, I think long enough, hopefully it will make sense. Stuff that's multiplying the same order has to be internally consistent. So this gives us our first equation, right? The stuff that I've written in red. So this would be equation 1 over here. We'd say 2c4 minus beta c3 equals minus beta t infinity, right? That's equation number 1. A little hard to see there. Equation number 2. So let's look for anything involving the x term. So here. On the left-hand side, we have beta c5 times x. On the right-hand side, we have nothing. So equation number 2 is going to be beta C5 times x equals 0. Equation number 3, we have stuff multiplying x squared. So now for 3, we have beta C4 x squared is equal to minus x squared over beta. Okay, so now I have 3 equations, three unknowns, C3, C4, and C5, and I can solve for them, right? And you can just take whatever the solution is and plug it back into your equation. That's your particular solution, okay? So this is the method of undetermined coefficients. You see now maybe why it's called that, because you just guess these coefficients, develop expressions for it, and then you solve for the expressions and plug them back in.